So accretion friction braking is when a object enters in the atmosphere of a large gas giant or young star or even an old star and is accreted. The material is accreted. It clumps together. Also, it's braked, meaning the material, it's traveling so fast that the atmosphere breaks it through friction. And we know this happens because we observe meteors in the atmosphere. What happens is large space rocks, which are called meteoroids or asteroids, mostly not likely asteroids. Asteroids are the big version of meteoroids. Meteoroids are the smaller ones. They enter into the atmosphere of a highly evolved star or a young star, and they burn up in the atmosphere. And this burning up allows it to disintegrate into little bits and pieces or even ionize and become its elemental form all the way down, to where it can be mixed up in the atmosphere and then combine with other elements. And this is very important because the actual accretion process that a star that requires, that planet formation requires, happens in a thick atmosphere of a young star. In outer space, there's nothing to give asteroids friction for the most part. Sure, there's some solar wind, but that's not really going to etch away at it very much. The majority of the etching, the majority of the destruction of asteroids and meteoroids happens inside the atmospheres of large stars. And large stars have large gravitational fields. They have huge masses. They have lots of atmospheric material to allow that asteroid or meteoroid to heat up through friction as it passes into the atmosphere. And a lot of those, they travel easily in excess of 45,000 miles an hour. So think of, I don't know if you guys want to look this up, it's kind of morbid, but the Space Shuttle Columbia disaster. When the Space Shuttle Columbia was re-entering Earth's atmosphere, the craft was, when it was entering, it comes in at an angle. The craft had some missing material on the heat shield, and that material, where it was missing, got heated up on the surface of the bottom instead of the actual heat absorbing material, and it ablated, and it's made this huge pit, which then started melting, and then it melted away the interior of underneath where the other heat shield material was, and eventually the whole thing just disintegrated from the inside out, and it just exploded in the atmosphere as it was entering in the Earth's atmosphere. And it happened over, I believe it was from California all the way to Louisiana. And that's one hell of a way to break up something if you want to mix it in with the atmosphere. And that being said, I needed to have a method for breaking up material so it can be recycled to form rocks and minerals. And I have a little rock and gem book here. Lots of cool stuff in this book. Most importantly, Adam, this is for you. We should always be aware that rocks and minerals are composed of elements in various combinations. And it's really, really neat because we have these weird combinations all over the place. Remanentite, check that out. Right there. I don't know if you guys can see that, but the chemical composition of remanentite is barium or water, manganese, and oxygen. So how did you get all those elements to combine with one another? They had to first be separate before they could become the remanentite. So naturally, what I think happens is those materials entered into a star when it was a more advanced stage, broke up, and then chemically combined with all that oxygen, with all that manganese, with all those other elements. and compounds to make more complex compounds, which then rain down in the interior of the surface of the star as it evolves, forming basically the ground that we walk on. Here's another good example. Altanite. See here, it looks kind of like sulfur. That chemical composition is calcium, and then you have uranium and oxygen, and you have potassium and oxygen, and then you have lots of water. So that's really cool. This rock has lots of water in it that makes up its chemical composition. Gypsum, I'm pretty sure gypsum has a lot of water. Gypsum has calcium, sulfur, and oxygen mixed with water as well. So it's CaSO4 times 2 H2Os. I don't know if you guys can see that. Let's see if it focuses in. Maybe not. But anyways, the reason why I have accretion friction breaking there is because that's how nature recycles itself. You have these rocks that are in outer space, the chondritic material, the non-chondritic material, the iron-nickel alloy, all the remains of smashed up dead stars enter into the atmosphere of younger stars. The atmospheres of the younger stars heat up the material, break it down into little bits and pieces, and it chemically interacts with a pre-existing atmosphere of that star, which then forms various, many, I would say, hundreds of thousands of different kinds of chemical combinations with that material. And then that material settles down into the interior of the star, depending on its mass, depending on its ability to be ionized, depending on its reactivity with other elements, depending on if it combined with oxygen early or late, whether it entered in the atmosphere of the evolving star in a reduced state or an oxidized state. And that's really complex stuff. And the evidence for this having occurred is in all the gems and minerals that we observe on the Earth. There's gypsum. And it's really wild, because when you look up things like this, like halides and all the chemical compounds that have formed over time, you never see in geology textbooks you never see the chemistry that happens to form the rocks and minerals to begin with. All they really offer you is what's called the rock cycle, meaning the rocks were pre-formed. So you never question how the rocks were formed. You just take the rocks, you break them down, and then you sediment them again as sedimentary rocks, or you squeeze them really hard and they become, metamorphic rock. But the rocks were already pre-formed. And it's really strange looking at it like that, because even rocks inside of a liquid magma state, they are composed of chemical combinations that are liquid rock. For instance, glass, silicon dioxide, I believe it's silicon and then oxygen. Sure, liquid glass, when glass makers, melt it down, it's still silicon dioxide. It's still, the same material that quartz is composed of. But they never say the chemistry of magma. It's just assumed just to be liquid rock, and then that's it. It goes off in the corner somewhere. Don't question that kind of stuff. And it should be a challenge for the readers to understand that, we have a huge amounts of chemistry that have occurred in the past, and we have the evidence for this chemistry having occurred because we have crazy formulas. I mean, look at this. Here's chabazite, a common zeolite mineral. Chabazite is a sodium calcium aluminosilicate hydrate. Hydrate meaning it has water on the end. It's composed of sodium, calcium, potassium, aluminum, silicon, and lots of oxygen. It has 24 atoms of oxygen just in that part. and then 12 hydrogen or H2O. So 24 hydrogen and then 12 oxygen as the hydrate on the end of the molecule. You can't just say that that type of material just formed in outer space because of gravitation. No, that's a major amount of chemistry occurring there. Where does the chemistry occur in outer space? It occurs inside of stars. The chemistry that makes the Earth's rocks occurred inside a very thick atmosphere of a star as it was cooling and dying. And that's what I'm going over right now. I'm taking chemistry right now, and it's pretty difficult, but I mean, I'm getting the hang of it. And being able to express rocks in the form of products from much simpler reactants is going to be a big challenge for me. But I just want you guys to see where I was headed with that. And this paper is the main reason, is because you have to have an ability for that material to recycle itself, and you have to remove the momentum, you have to remove the pre-existing chemical combinations so they can be recombined into various other forms, and you also have to provide a place where there's a lot of heat and where there's a lot of pressure, and that exists inside of the thick atmospheres of highly evolving stars. Alright, you guys, today is January 31st, 2019. I just wanted to show you guys where my mind was at. Later.